Okay, so let's continue. So just a little speech I just gave before the break for to motivate you to ask questions was very helpful, and there were some very nice questions in the break. So let me now repeat my responses to those questions. So one of the questions was, what is this state space presentation anyway, and why we are doing it? Okay, so let me. Okay, suppose that we have a system and this is the differential equation. Okay, so if you remember what we did before this topic from the beginning of the semester, we said that if this system is linear, then this equation Okay, so if this şeyi açtık mı ya? Okay, so it's recording. Okay, so we said first, if our system is linear, then the differential equation is actually in this form. It's a linear differential equation, and then we can take the Laplace transformation of this equation and obtain a transfer function. Then and obtain transfer function. And then from here, we can analyze the system more easily. That means we can find the response to various inputs or the response to initial conditions easily. So that's why we use Laplace transformation. Okay. Now, this state space approach is yet another approach to make the system analysis easy. Okay. So this was one option. So now let me do the following. Let me just copy everything here and then condense it here a little bit. So this was one option. So we went from here to here, and now I'm saying that another way is to take this equation and write it in terms of state space equations. I'm afraid I don't have a general. From here, in addition to this, I need to have state equations. Let me see if I have. Bunu şeyden kopyalayayım en iyisi. Okay, so these are the state equations. Let me make them smaller. The state equations, and then I should add the output equation. Okay, so this is an alternative to studying the system. Instead of going through the Laplace transformation approach and working with S-domain functions, you can keep working in time domain and instead write n first-order equations. So this approach makes analysis very easy if you are doing numerical solutions. So if you have a computer, then instead of integrating an nth-order differential equation, it is easier to integrate n first-order equations. Okay, so this is where we are. We're still working with systems. So this goes to S domain, and this goes to this is time domain. So this is an important thing. This is valid only if your system is linear, and I should make this big. But this state space representation is valid for even nonlinear systems. Your system can be nonlinear. Okay, so if you are doing numerical simulation, if you are solving the system equations numerically, then this way will make it easier. And also there are some analytical tools that can be used without computers that are applicable to state space models. Okay, so that's why we're talking about the state space representation. So it can be nonlinear. That means in that case these state equations will be nonlinear, just like the pendulum example. Let's remember that here the state equation is nonlinear because we have this trigonometric function here. But obviously, if our system is linear, then it provides or it brings certain additional simplifications. So let's now take a look at that case. Now let's consider what happens if our system is linear. State space representation can be used for nonlinear systems as well, and for linear systems state equations can be written in matrix form as follows. Okay, so if the system is linear, then the original equation should be in this form. So in this case, we define n state variable as functions of these terms. So here how we define them. In fact, I think we have these in the lecture notes, right? So in the lecture notes, there's a mistake actually. So we shouldn't have the highest derivative of u here. So I should make this correct. So this should not be here. Since our system is linear, obviously the state variables should be defined as linear variables. So that means these should be linear functions of y and y dot and all the derivatives. And these should be linear functions or linear combinations of these things. Okay, so let me, I can already start writing this in matrix form, right? So I can make a huge x vector, x1, x2, all the way up to xn on the left hand side. And on the right hand side, I have these things, h11, h12, h1n, and I have hn1, hn, y dot, yn dot, or not n dot, right? Y to power n minus 1, or the n minus first derivative of y. Then plus there are some u terms. Okay. This is an n by n matrix. And this is an n by m . Okay, so before I told you that all of these derivatives should be represented in the state equations, right? So for linear systems, this means this n by n matrix you have here should be an invertible matrix. It should have full rank, in other words. Yazayım ya, üşendim ama. to be represented in the above and by n matrix. Also in the linear case, okay, so let me just fix it. It's not entirely true. So all of this should be represented in state variables. For linear systems, state variable definitions bundan sonrasını type ederek devam edeyim. State variables for this system, state variable definitions are made as shown above, where we define a n times n matrix this square matrix has to be invertible. That means it should be full rank, which also means its determinant should be non-zero, right? So these are all, they all mean the same thing. Okay, so if you go back to this example, so here's how I define them, right? So if you look at this definition from here, the definitions were x1, x2 is defined as 1, 1, and 0, b, y dot. So for a non-zero b, this is invertible, right? Because the determinant will be non-zero if b is not equal to 0. But if you remove y here, then that means this element will be 0, but obviously this has a 0 determinant, which means you cannot take inverse of that matrix. So this is not a valid state variable definition. Okay, so I'm going to take all of these back. Okay, so if we have a linear system, we choose our state variables as linear combinations of all these terms, and then for state equations we need to differentiate them. I guess I skipped a step in between, so let me just complete that step here. So the state equations are the first derivatives of these state variables. So I obtain them by differentiating these equations. This is x1 dot, this is x1 dot, and this should be y dot, y dot, y double dot, and this should be the nth derivative. Similarly, so is this the nth derivative, and I have similarly u dot and u dot. Okay, so this is how I obtain state equations. Next, I write y dot, y double dot, and y the nth derivative. In terms of the new state variables x1 and x2, and since the system is linear, these will be linear functions as well. As well, in this, in the end, state equations become these equations. Okay, so this can be written in matrix form as follows: x1 dot up to xn dot u, and the output should also be a linear function of these state variables and the inputs. C1 Cn times d1 and dn. So these are different numbers. They don't have to be the same numbers as before. Okay. So we call this A. It's an n by n matrix. So this matrix is called B. It is n by 1. So C matrix, which is 1 by n. And C should be dn, right? So we let's do it like that. And we call this x vector. So this is x n by 1 vector, and this is x dot. That's also n by 1. Okay, so for linear systems, the state space equation can be written in matrix differential equation form as follows. We have x dot is equal to a x plus bu y is equal to cx plus du. Okay, so these are the so this is a vector first order linear differential equation. Okay, so these are just matrices now. So this is an n by n matrix, this is an n by 1, and so are these, they are all matrices. And for numerical solution, this increases the efficiency. So you can, if you are doing numerical analysis, then this form is better to work with instead of the original nth order equation, like this one. Instead of integrating this equation, it's easier to integrate these equations. And also there are some very powerful analytical methods that are applicable to these set of equations that are in this form. Okay, so we have some analytical tools as well that we can use for such systems. That's why the state space approach is very powerful. So as I said, this is another way to study systems. So first we talked about Laplace transformation, and we said that if you take Laplace transformation, you get transfer function in this form, and then you can analyze system in that domain. So this is what people were doing at first. So this is called classical control. So whatever you do in S domain is called classical control, and this was developed before the Second World War. So in the 30s and 40s, 50s, people were designing controllers using this approach. But then after the advancements in computers, it became easier to do numerical integrations, and so these, or the methods based on state space representation, they were developed after like 50s and 60s, and this is called modern control. So in the modern times, so this was fully developed in 70s, 80s, 90s. So people started working with state space models since they already had these powerful computers. Okay, so this is the old school, and this is called the modern control. So nowadays, the state space representation is used more widely than the state space or the S domain transfer function representation. Okay. So if your system is linear, the state equations turn into these equations. But if your system is not linear, then your state equations will look different. And they are all somewhere here. Okay, so in the most general case where you have a non-linear and time varying system, state equations will be in the form x naught is equal to some nonlinear function of x and u and time. This is again a vector differential equation. Okay, so here x is again a vector of state variables, and f is a vector function f1, fn, and you have the output equation. If the system is nonlinear but time invariant, so the equations are in the following form. Only t is missing, right? Since it's still nonlinear but time invariant, there should be no explicit time dependence. So the equations are in that form. If the system is linear but time varying, state equations are linear equations, but they are time varying. So you have x dot sum is equal to some matrix, n by n matrix, which can be a function of time, times x plus p of t times u. Y is equal to c of t times x plus p of t times u. And in the simplest case, when it's both linear and time invariant, then you have all these matrices as constant matrices. Okay. Okay, so a very important benefit of the state representation oraya bir kelime düşünüyorum, aklıma gelmedi ya. Avantajı ortaya çıkar falan diyeceğim de. Representation okay, so let me just continue and you will hopefully understand what I mean. This representation is observed for multi-input and multi-output systems. When working in S domain, we have a transfer function for a single input, single output system, and a transfer function matrix for multi-input, multi-output systems. In state space, for MIMO systems, for linear and time invariant, which is abbreviated as LTI. P, let's say. now we have many inputs, right? So we have P inputs, let's say UP. Okay, and if we have multiple outputs as well, then we should modify this equation for that. No, 1n. Two. And we have multiple inputs as well. It's 2 times n. Okay, so these are the linear state space equations for MIMO systems. Okay, so additional inputs add columns to the B and D matrices, and additional outputs add rows to the C and D matrices. But the A matrix does not change. Okay. So this makes state space models very useful and powerful for multi-input and multi-output systems. So this is another reason why these state space models became very powerful after the Second World War, because the systems were getting more and more complex with multiple inputs and multiple outputs, and for such systems the state space models are very easy to work with. Okay, so if you have a computer program that can already integrate a system in that form, just adding columns to it or adding rows to these matrices doesn't really make that much of a difference. So it's just very easy, very simple addition, or going from single input, single output system to multi-output is just very straightforward in the state space case. Whereas if you want to do that in the transfer function approach, then you go from having a single transfer function to a transfer function matrix, and that complicates the things a lot. Okay, so the classical control is for SISO systems mostly, and the modern control can handle both SISO and MIMO systems. Okay, and then there are some like robust control techniques which combines the two. So which combines classical control and modern control techniques together, but that's really well beyond the scope of this course. Okay. So, any questions? Ha, U değil aslında ya. Nerede dedik ki onu? Okay, so let me tell you what we have to do. So if I said something wrong, I should correct that. So are you talking about this one? So we should write all these derivative terms in terms of the state variables and u. But u is u itself, so you don't need to write u in terms of anything else. So in your state model, you should have x and u only. So there is no y or y derivatives or u derivatives. Okay? That's a good question, and I think the easiest way to explain that is on an example. So let me give you an example next time for tomorrow that includes u derivatives, and that way you can see how you get rid of the u derivatives by defining state variables properly. Okay? Başka sorusu var mı arkadaşlar? Biz yine süremizin sonuna geldik. Yarın görüşürüz. Nereden kapatıyorduk ya?